You saw the thumbnail. Is it possible for e to the 1 plus z squared plus z cubed and so on forever to equal -1? Let's get stuck in. We see in the exponent here we've got 1 plus z squared plus z cubed. This is what Black Pen Red Pen refers to as his best friend. And this thing here is a nice convergent series. It equals 1 over 1 minus z. Now, I'm not going to go into why this is true. If you've not seen geometric series before, I'd encourage you to have a look or a little bit of research yourself. This is what this formula equals, but we have to bear in mind that this is only valid if the magnitude of z is less than 1. So if the magnitude of z is less than 1, then 1 plus z squared plus z cubed and so on forever equals 1 over 1 minus z. It's just a geometric sum. Now, if we look back to the original equation up here, we want the right-hand side to be -1, which is a negative number. So if there's any chance of this even being true, we need this thing here to be a complex number because we know e to the power of a real number is always a positive and so wouldn't be able to equal -1. So therefore, we must be dealing with z being a complex number. Okay, so z's a complex number, not an issue. This formula still works if z is a complex number. So we've got e to the 1 over 1 minus z equals -1. And now we need to think, well, what's -1? Here's where we can use Euler's identity. Euler's identity says that -1 is the same as e to the pi I. So e to the pi I is the same as -1. And in fact, we can generalize this to Euler's slightly ugly sister formula, e to the pi plus 2n pi I. So -1 is still e to the pi plus 2n pi I. It just looks a little bit less nice because you got this n in there, but that's fine. N is just an arbitrary integer. So we get e to the 1 over 1 minus z equals e to the pi plus 2n pi I. Getting rid of the e's on both sides, we get 1 over 1 minus z equals pi plus 2n pi I. Now, if I kind of cross multiply or kind of bring this into the denominator here and bring this 1 minus z here, this equation becomes 1 minus z equals 1 over pi plus 2n pi times I. And if I multiply the top and bottom of this fraction by minus I, this just becomes minus I divided by pi plus 2n pi. Okay, cool. Now, if I rearrange this for z, I get z equals 1 1 plus I over pi plus 2n pi, like so. Okay, does that solve our problem? No, it doesn't. In fact, this proves that there are no solutions to our original equation. Why not? Well, remember we used this formula over here, but in order to use this formula, we need this condition to be true. But what we've just shown is that z would be 1 plus I over pi plus 2n pi. But what's the magnitude of this guy if I just squeeze it on here? The magnitude of this is just the square root of the real part squared, which is 1 squared, plus the imaginary part squared, which is 1 over pi plus 2n pi squared. And it's pretty clear that that is going to be at least 1. In fact, it's going to be strictly bigger than 1. And so therefore, it does not satisfy this requirement. And so we cannot use this formula. This thing here, in fact, diverges. And hence, there are no solutions to this equation here. And that solves our problem. I hope you have enjoyed this one. Thanks for watching. I'll catch you in the next one. Have a great day.